Minimal spanning tree. There it is. If that little thing would go away. Okay, come on back. You can do it. This computer isn't the fastest.
Versus the other ones right at the school.
Versus the other ones at the school, yeah. Yeah, exactly. Okay, we want to go right there. You can do it. You can do it. Minimal spanning tree. All right, we started this already. We came up with the problem was to find a subset of the edges that that's a tree that spans the graph, meaning that if you could get between A and B before you can get there with the edges that you've taken. And the algorithm is just to grab the best edges. You sort the edges based on their weights, and you look at them in that order, and you take the next edge, assuming that it doesn't create a conflict, which in this case is a cycle, right? Because we want a tree, right? And then you have to prove that yes, this spans the graph, and it's minimal. All right, let's keep going. Come on, come on. Whoop. There's the code. All right, so when you're doing this, you want to first say, be really clear what the objects are. Here, the objects are edges with weights. And what a solution is a subset of the edges that spans the thing and is a tree, and it's minimal cost. The cost of a solution is the sum of the weights that you've taken. So when you read the question, ask yourself those questions. What are these pieces? Because really, it may sound silly, but the number of people who just get a bad start on the question because they don't know what the parts are, it's too high. Then you need a paragraph which says, okay, we're going to prove that this algorithm always gives you the optimal answer. Right? In some ways, it's an amazing statement. It says, for any graph, whenever there's choices about how you sort the things, this thing will always give you a minimal spanning tree, right? And so we need a loop invariant which says we haven't gone wrong. We're at the top. The algorithm's at the top of the loop. It's committed to some of the objects so far. It's rejected some of the edges so far. We know that there exists an optimal solution that's consistent with what the algorithm has done so far. What does that mean? The algorithm is only committed to a few edges, so the algorithm doesn't have a full solution. But there's some full solution which is consistent with those ones that the algorithm has done, and it is valid, meaning it has no cycles and it's optimum. Right? And we're assuming that the fairy godmother is holding it. How do we establish that? Well, initially the algorithm hasn't done anything, so any optimal solution is consistent with it. Now here it's a little tricky. In this case, you have to be sure that there exists a solution. Often the empty solution is good, but here it has to both span the tree, right? Span the graph and be a tree. But it's not too hard to convince yourself that there are such solutions. All right, so now the hard part, we went through these steps here, and we're, by the loop invariant, we know there exists this optimal solution which we've given this name. By the X condition, we haven't stopped, so the algorithm grabs the next object, next edge, and either commits to or rejects it. Then we assume the fairy godmother is holding this optimal solution. We tell her how to massage it to this optimal solution. Then she's holding this. We prove that this thing here is valid, optimal, and consistent, and we're good to go. We proved that to loop invariance. Everybody get the steps? Really, make sure you ask questions. In fact, I was here during the TA. She was writing on the board, and you guys were sitting there, just like you're sitting there now. And it seems to me that if you're going to learn anything, we have to talk a little bit more. So.
I was the only one talking.
Good. Good. It's true. All right. So she's holding this optimal solution, right? He commits to the next edge. I'm going to instruct her how to change her optimal solution, right? So let's go through how to do that. there's some big graph here, right? And I'm not drawing the entire graph because if the more we draw, the more we don't, because we don't know what the input is, right? So we want to keep it as general as possible. There's some edge here, and that's the edge the algorithm just committed to, right? She's holding a solution, right? We say, hey, fairy godmother, you just added an edge, right? What's possible? It's possible she has that edge already, right? Then what do? Everybody get that we do nothing? Because then she has an optimal solution consistent with what was done before and consistent with what the algorithm just did, and we're good to go. Right? Everybody get that? So if she has that, we say, great. Right? But otherwise, what do we know about her solution? We know it spans the graph. Right? And we know, we can see this yellow edge, so we know that in the original graph you can get from U to V. Right? So we know that in her solution you can get to U to V. If she didn't take this edge, then what do we know that she has? She has some other way to get from U to V. Right? So think about this other way to get from U to V that she's taken instead. Right? Everybody good with me here? We're just kind of logically thinking what the fairy godmother must have and telling her how to change it. Right? She must have some solution there. All right, so what are we going to tell her? We need instructions to her. What are instructions going to be?
Drop the rest.
Right, just to take this one, and she'll drop something. Which one should she drop? All of them? No, because they might be really useful.
The last one.
One of
Let's just tell her to drop
one of them, and then you get these.
the last one according to what? Yeah, well, let's tell her to drop the most expensive one, right? First off, is it possible that the algorithm has already taken all of these? No, why not? Because we took this edge, right? The algorithm took this edge, right? So we know that the algorithm might have committed to some of these already, but hasn't committed to all of them. And so there's something that she's committed to that we haven't. And we could say drop the most expensive one, but the truth is, I think we can say drop any of them, right? I don't think it even matters, right? We just tell her to drop something. Everybody get our instructions? Now what's key about these instructions is that they're in a nice little paragraph where I can read them and I can know what your instructions are, and the fairy godmother can read them and she can always do them. Right? Oh, the marks are posted on the forum on that program. And those of you who don't have the right CS account and stuff can't read them. So if you want to talk to me, we can somehow get you your mark today. You have to get your mark, you have to be registered in the class with the correct sort of email. So I know that there are people who don't fit that. All right, so the instructions to her were, take this guy and drop that guy. All right, so she's putting this one in and she's dropping this and she's dropping that one, right? Because the algorithm didn't take it. Everybody got the algorithm? All right. Now we have to prove that what she's now holding is consistent with what the algorithm has done. All right? Well, what she was holding before was consistent, meaning it had the edges that the algorithm is committed to. It doesn't have the edges that the algorithm rejected, right? So we changed it to this. We want to make sure the same is true. Right, well, what do? We told her to add an edge. Well, this isn't one that he'd rejected because he's just about to take, that makes that guy consistent. That's good. We told her to drop this one. Well, we made sure the algorithm wasn't holding it. Right? The algorithm hadn't considered this guy yet. So everything's good. Right? So we need to prove that it's valid, meaning it has no cycles and it spans. All right? Well, what she had before was spanned and had no cycles. We put this edge in, which created a cycle, but we broke that cycle, right? So it still has no cycles. How do we know that what we have there still spans the whole graph?
Because you can still get to any.
Yeah, how are you, I mean, suppose that you could get from here to here. I think we might have even had this somewhere. Let's see. Okay, we're giving an example before we move on. Right? Suppose the algorithm is committed to those edges. She's committed to those edges, right? See, this isn't a full solution, right? That's just what the algorithm has done. She has more. The algorithm takes this 2. So what do? We tell her to drop this 2. Right? I don't know why it does that sometimes. It's kind of annoying, but whatever. Just doing the... All right. Now we're going to prove that what she has is acyclic and spans everything, right? What she had before was acyclic. We added an edge. We broke the cycle. So we're good. Prove that it was spanning. Well, what she had before connected every 2 pairs of nodes that were connected, right?
The diagram that you showed previously, what's happening in the smaller circle? Smaller triangle circle.
Oh, here?
Yeah.
Oh, this is, here we're trying to say, in general, you'd think that the input is going to be connected. And so, to be spanning, it has to connect everything. But the original graph might not be spanning. And so, an optimal answer will connect everybody that you could connect before. So she had this solution. The algorithm is committed to this. She has this solution. But then the algorithm took this edge. So we tell her to take this edge and to drop this edge. That was just another example. Does that make sense? Good question. All right. All right, what she was having was spanned the graph. So that she can get from here to here from with what she had before. Right? But we told her to drop this edge. So how is she going to get from here to here? She's going to go this way now. Right? Does that make sense? So it's still spanning. Now, how do we prove that it's optimal?
It's already optimal.
It was optimal. This was optimal. And what do we have to prove?
That this is not bigger than that.
Right, we have to look at this edge versus this edge. We have to prove that this edge is at least as cheap as this edge. Right? How do we know that this edge is at least as cheap as this edge?
It's the algorithm.
Right, because the algorithm considered this one first. Right? Right? The algorithm took this edge over this edge. Right? And hence we know, right, that we added this one and replaced this one, so our costs changed by that. Everybody kind of following this? And so the optimal solution gets better. So this was optimal, and so the new thing is optimal. Right? Everybody following this? Now, and remember, when you're writing this up, I keep saying this, but I don't want to read wrong answers. Right? Remember what these things are. Right? Never say, I have this. Right? You don't really have it. You know, the fairy godmother still has it. So keep track of who has what. Everybody kind of good? Right? Oh, so another point here is, you know, it couldn't have really gotten better. If the fairy godmother is holding an optimal solution before, then it couldn't have gotten better. So really, these two weights have to be equal. Right? So anytime you could have swapped, then they must have been equal. So this was a question, at least on an assignment. Maybe it wasn't on a test. I can't remember. But it's a fine question. Question is, suppose I give you a graph where all the edges are unique. right? You don't have two edges with a weight of 2. They're all unique. Is there more than one optimal solution? Right? There's not. Why? Because, well, if the fairy godmother was having one, it would never switch over to another. Right? Because she could never make a change like this. Right? So she would never actually change what she's doing. So in the end, whatever optimal solution she started with is the optimal solution she'll end with, which is the optimal solution the algorithm will return. Does that make sense?
For these graphs, do these only work with positive numbers? Or do
Good
they work with
question.
negative?
So Dijkstra's algorithm only worked with positive edges. This algorithm here works for anything, any edges. They can be negative, they can be whatever you like. So you can have multiple solutions only having from multiple edges. All right, so then we prove that this thing, we loop invariant assume this. From that, we showed that there exists this, which is valid, consistent, and optimal, and hence we've maintained the loop invariant. Everybody good with that? Everybody can see what these paragraphs are? Everybody memorizing these paragraphs? Everybody's going to give me these paragraphs? Good. Right, so we maintain the loop invariant. That's case 1. Case 2 is that the algorithm rejects an edge. What's going to happen in this case?
They don't even drop it.
Did the fairy godmother, does she have this edge that we just dropped?
She should be.
She should. And why can't she have it?
Because it doesn't fit the algorithm.
Okay, what she's holding is optimal. Well, it doesn't matter it's optimal. What she's having is consistent with what the algorithm has. Right? So if the algorithm has this and is not taking this edge because it creates a cycle, it means she has this and she better not take that edge either. Right? Does that make sense? So that's usually the way case 2 goes. And then, how do we clean up? Well, the exit condition tells us we made a decision about every object, and hence the algorithm has a solution. Right? The loop invariant says there exists an optimal solution consistent with the solution. Well, if it's consistent with the solution, then it is that solution. And if it's optimal, then life is good. And we return that, and we go home. Everybody happy? All right. Let's cross those down again. Oh, the time complexity. Well, you have to, again, you consider every edge, right? Right, you sort the edges. Actually, what is one of the bottlenecks in this algorithm? We have all these edges. What's the first thing we do with these edges? We sort them. All right? So that right there is going to take E log E time, right, to sort them. Now, the other part is for every edge. What do we have to do with every edge? And we reject it if it creates a cycle. So how do we know whether it creates a cycle, right? How do we know if it creates a cycle? You put that guy in here. Well, somehow you have to say, did that create a cycle? In this case, it didn't. We put this one in, you have to know it created a cycle. I mean, it's not so easy, right? So, we need a cycle detection algorithm. In the algorithm, we're going to have this loop invariant, something that we're going to maintain. We're going to maintain sets of edges. All right? And the sets of edges will be, these are all the edges that, the sets are all the connected components. Right? We'll know that this is one connected component. This is one connected component by itself. Right? Everybody get that? And then, when we add an edge, if it's in the same connected component, then what do we know? We have a cycle, exactly. And if it bridges two connected components, where's our bridge? There it is. If it bridges two connected components, what do we do? No. Doesn't create a cycle, and what do? Is we merge the connected components, right? So what do we need? We need a data structure that has, we start off with n objects, each in an individual set. And what we're allowed to do is we're allowed to take two of those sets and merge them together. And we're allowed to name an object. Actually, we name two objects, and it'll tell us whether they're in the same set or different sets. Right? In fact, what you do is you take an object, and it'll tell you the name of the set that it's in. Right? So now for the two of them, you say, what's the name of the set that this guy's in? What's the name of the set that this guy's in? You see if they have the same name. Right? Does that make sense? So the data structure, we could spend a lot of time talking about it, but we'll just give a quick proof by picture. All right? So for every object, all the n objects will have a little record, and it's able to point to one other record. All right? And this is a connected component. You see they just all kind of point up, and then we'll be holding on to this guy, which is the name of the set. Right? So now what are the various operations? An operation might be, see, him, what set is he in? Yeah?
If you go back a few slides first, I'll just cycle. It's minor, but I mean,
What?
go back a few slides. There's a cycle in the main chunk.
Okay.
GCV, HCV.
Yeah, there is.
I think it's okay.
Yeah.
Good. There is a cycle there. Yeah. All right. I'll try to remember to remove it. All right. So here, so we have a pointer to each of these objects. So if you say, "Hey, node E, where is it?" So you go to node E, and then you follow the pointers until you get to a dead end, and then you know that's the name of the set. Right? People kind of get that? And now when we merge them, we have this guy and this guy, we merge them together. We just have one of them point to the other. Right? And that merges them. Merges the set. Now the problem with merging is then they get deep. Right? If they're deep, the problem with them being deep is now then we do a query, it takes too long. Right? So when we do a find, one of these queries, we're going to, as we do it, we're going to do a little extra work, and we're going to collapse the tree. All right? So what if we're looking for, what are we looking for? Find W, right? How do you find W? Is you follow the links up until you find V, right? And then we're going to do it a second time. We're going to hold on to V. We remember V. And now as we go through again, we point W at V, D at V, A at V, U at V. Right? And that, in some ways you think, well, that doubled their time right now. But, you know, we don't care about factors of 2 anyway, so the fact that it doubled their time isn't a big deal. But it collapsed their tree. Right? So the next time you do queries, the tree's smaller. So you'll never get charged for that height more than once, because you're collapsing the tree as you go. All right? So here's an amazing thing. Suppose that you start off with this data structure where they're all individuals, nodes, and you can do as many queries and as many unions as you want, right? Using this data structure we just described. The question is, now some operations, like this operation right here, might be expensive, right? Sometimes you might have a high cost. But the amortized cost is what is the average over all the operations you could possibly do, what is the average cost, right? Because here, well, this operation costs a lot, but how did we get there? We had to have a lot of operations to build it up. And then if you do something later, then it's smaller, right? So the amortized cost when you have n objects. Anybody want to guess what the worst case amortized cost is when you have n objects? We would like to say, ideally what would it be? Just a constant, right? Ideally it would be a constant, it's not. So, I told you this once before what this time is. It's Ackermann's function. In fact, I think I can probably put it right up here. inverse Ackermann's function. Remember Ackermann's function? Ackermann's function was the one where Ackermann of 4 was bigger than the universe. Right? So this says that if your input, if the number of nodes you have is bigger than the universe, and you do as many operations as you want, then it may cost you 4 operations per time step. Right? But if you have fewer nodes than the number of atoms in the universe, then the amortized cost will be less than 4. Yeah, so that's pretty good. For all practical purposes, it's a constant. All right, back to... all right, so what we did already was we did Kruskal's algorithm. All right, now we're going to do Prim's algorithm. Prim's algorithm is we're starting at some node S, and maybe we're searching the World Wide Web, and we're trying to find a minimal spanning tree, but you don't know things exist until you discover them. All right, so what we're going to do is we're going to span from S, keeping the best, always taking the best edge that's connected to what we know about. All right, so initially, what do we know about? Initially, we know about these edges. So what edge do we take? We take the 1. Now what do we know about? We also know about these. So we put these into the heap because we know about them now. And now which one do we take? Right, we take one of the 2s. We take that 2 up there, which puts these guys into the heap. Now we take the one that looks best. Right, now we can take one of these 1s. Right, so we take that 1, which puts this into the heap. And then we take this 1, which puts these into the heap. And then we take one of the 2s, which puts these into the heap. And then we take one of another 2. Oh, we take a 1. There's a 1 in here. I forgot about it. Right, which puts those guys. Oh, we can't take. We're trying to take that, but it created a cycle. And those all create cycles. Everybody get that? What about these? We never know they exist, so we ignore them. Everybody get the algorithm? And so here's a question: is this a greedy algorithm? Remember, what was a greedy algorithm is you take at the beginning, you look at every edge, and you decide whether you like it or not, and you sort them with respect to those edges, the criteria. Right? So is this a greedy algorithm? No, because their priorities change as we go along, right? So this is what we call an adaptive greedy algorithm, that every step before you take the next object, you can update your greedy criteria. So in a fixed priority algorithm, you sort the objects from best to worst once and you loop through them, right? In an adaptive one, the greedy criteria depends on what you've committed to so far, right? And so each step you take the best one according to your current greedy criteria, and then you're allowed to update the criteria, the priority, right? And so then what data structure do we want, right? Do we want to resort every time we update the priorities? Do we want to resort them? No. What data structure are we going to use? A heap. Exactly. In fact, I said that. You add these to the heap. You use some kind of priority queue, which is a heap, right? And so what's this adaptive greedy algorithm, right? The input is a set of objects, and the output is you make some decision about each of them. You put the objects in the priority according to your initial greedy criteria, right? So initially, in that algorithm, we only know that the edge is connected to S, and we put those into the priority queue. And all the other objects, what do we do with all the other edges? They kind of have priority infinity. You can stick them in there as well if you want, right? And then we've committed to no edges, no objects. The loop invariant is the one that we know. There's an optimal solution consistent with what we've done. We exit when the priority queue is empty. We take the best object out of the priority queue, we decide whether to commit to it or not. Generally, if somehow it doesn't conflict with what we've committed to already, in this case it doesn't create a cycle, then we commit to it. People following this? Right? Otherwise we forget it. And then we're able to update objects in the priority queue. And those objects that get updated either bubble up and bubble down. Right? And this is an adaptive greedy algorithm. There it is. So Dijkstra's algorithm, right? We all did Dijkstra's algorithm. If you think about it in the right way, it's a dynamic greedy, an adaptive greedy algorithm. All right. All right. Is everybody good? Any questions? Anybody not following what we're doing? Don't be shy. Don't be shy, because I'm gonna know in a week.
The last part, that whole last part.
The whole last part you didn't get?
Yeah, that whole
Do you have a question about it?
I don't know if it's really a question or make it more palatable.
More palatable. All right. So do you understand what greedy algorithms are?
Yeah.
Right? You look at each object, you give it one priority, you sort them, you go through them in that order. Right? So this is the same, except you get to change the priorities as you go. So you start with some initial ordering, and then you take the best object from the beginning of the priority queue, and you decide to keep it or not. And then based on the fact that you've looked at this, you can go in and change the priorities of some of the other objects. All right, so let's do an example. All right, so initially, I'm here, what do I know about? I know about these edges, right? So they're on the priority queue. These guys, all the yellow edges, have priority infinity, or I don't even know about them, right? So now I say, give me the best guy on the priority queue. It's going to be this one. But now I've discovered, so I take it. But now I've discovered these, so I add these to the priority queue. So now what's on the priority queue are the orange edges. Right? Does that make sense? Now we say, give her its best from the priority queue. It's going to be this guy. We take him out of the priority queue. We commit to him. And then these guys go into the priority queue. Right? They go in. And we keep going like that.
And you take the best of that.
Right. Then we take the best, and then we add to the priority queue. We take the best, we add to the priority queue. We take the best, we add to the priority queue. We take the best, we add to the priority queue. We try to take the best, but it creates a cycle, so we throw it away. All right? So the proof, we're not going to do the proof that algorithm works, because the proof is really identical to our previous proof, and let's not waste our time.
For the adaptive stuff, could you end up with a situation where you picked one route, things changed, and then you would create a cycle by taking it, but it would actually end up being better if you were to undo something that you had taken before? Because of the changing.
Yeah, so if I get the question right, I mean, in general, greedy algorithms, the danger is that you commit to things and you go wrong, right? You take that 4-cent coin, and that was a mistake, right? So for most problems, if I gave you a generic sort of optimization problem, what's true about this optimization problem? It's likely NP-complete, which means there's no polytime algorithm for it, and this a greedy algorithm certainly doesn't work, right? So in this case, right, it happens to give you the right answer. Yeah? All right, so let's do one more example here. I think this is going to be our last greedy example, which is actually good because I looked at our timetable today, and Monday is scheduled to do greedy algorithms, and then we're supposed to be done greedy algorithms. So if anything, we went from being behind to being ahead. So feel free to ask lots of questions. All right, so here's our problem, all right? The input are a bunch of points in a line, and a bunch of intervals of the line, right? And our goal is to choose a subset of the intervals that cover all the points. All right, does this make sense? Right, and what the cost is going to be, take as few intervals as possible. Right? The smallest subset of intervals that cover all the points. Great. So what's the obvious greedy algorithm? Is you take the edge that covers as many points as possible. Right? That seems the obvious, but it doesn't work. All right. So everybody see this example? Right. This was our input. What's the obvious interval to take? It's this one here. Right? It covers the most points, but it's not optimal. Because if you take it, you still need this one and this one. Right? Does that make sense? So then you would have to take all three. And actually this algorithm, if you were going to do it, is I think it's 3 optimals. You get an answer within 3 of optimal. All right. Anybody want to name another greedy algorithm? You did well last time. Greedy algorithm.
Say it.
Sure.
The one with the. Well, we're going. It has to cover the first point and it goes as far as possible.
Yeah. Yeah, exactly. Right? Here's the algorithm. Consider the leftmost uncovered point. Right? We need to cover it somehow. Right? So let's only consider intervals that cover it. And of the intervals that cover it, let's be greedy. We might as well go to as far as right to as possible. Right? So of these intervals cover it. So take that one. Right? Everybody got that? So we do it again. Take the node that's the leftmost node. I always have to make sure I know my left and right. That's what I was doing there. The leftmost node that's uncovered, we have to cover it. Who can cover it? They can cover it. Right? Which one of those should we take? The one that goes furthest to the right. Right? Leftmost uncovered point, who, grab those, furthest to the left, furthest to the right is that one. Right? We have to cover this, those can cover it, we go furthest to the right, and then that's our answer. Everybody got the greedy algorithm?
So you're allowed to overlap.
Yeah, they're allowed to overlap. Yeah, they're not, it's not intervals, like, it's not scheduling.
Instead of taking the top one, wouldn't it be better to take the little one in the second column? The second row? Don't take the very top one. Back down.
Yeah.
Take the one right below it. No, beside it.
Yeah,
Yeah.
this one. I think this is good.
Because then you have a smaller...
Well, there might be other optimal solutions, and there may be ones with smaller edges, right? But here, our only thing we care about is the number of intervals, right? So this has 4, and I'm claiming that there's no way to cover the points with only 3, right? So certainly, if your measure of your cost of your solution was the sum of the lengths, or you wanted to minimize the overlap, right? Then that would be a whole different problem, and then you'd probably certainly a greedy algorithm wouldn't work. You'd have to go up to dynamic programming, and if you twist it at all anymore, then it becomes incomplete, right? Then there's no algorithm for it. All right, so is this an adaptive greedy or a non-adaptive greedy? Do we take the intervals and sort them in some fixed way? No, it's very adaptive. It's adaptive, and based on what we've done so far, the edges we're going to consider are those that cover the next point. And of those, take the guy who goes furthest to right, right? This is very adaptive. Everybody got that? All right, so now we're going to prove that this algorithm works. All right? Everybody ready to prove it works? Okay, what's the first paragraph? The first thing you do is you make sure you understand the problem. Second, you make sure you understand the algorithm. How do you understand the algorithm? You have to know the sort of the greedy criteria. Given that we've done this so far, which object do we do next? And then, given we've chosen an object, how do we decide whether to take it or not? In this case, how do you just always take it, right? You grab the next one that you like and take it. Now, and then the proof that the algorithm works, the first step is you say what our loop invariant is. And the loop invariant is, that there exists an optimal solution consistent with what the algorithm has done so far. Sound familiar? All right. And then then a new paragraph. How do we establish the loop invariant? Well, initially we haven't committed to any intervals, right? So any solution can be consistent with this, right? So then we go through these steps. Everybody remember these steps here? Should we go over them again? All right. So suppose that our little brother here has committed to these intervals, right? The fairy godmother is saying, I'm holding a full solution, 5 minutes, thanks, a full solution that's consistent with this solution. Right? Everybody get that? Get the difference between what the algorithm is holding and what the fairy godmother is holding? Right? She's holding a full solution. Then, the algorithm looks at the leftmost point and considers these intervals, right? And then he takes the one that goes furthest right, right? Now, if now I'm going to have to tell the godmother she's holding this. I have to tell her how to massage it into this, right? So how am I going to do that? Well, you'll note she didn't take this one. I say if you took this one, good, we'll go home, right? If you don't take it, if you took something else, oh, she took something else, right? In fact, maybe that's even what you wanted her to take. I don't know. What do? We tell her, take this one, right? So we know that she has some interval that covers this point, right? So we say, fairy godmother, you cover that point somehow. In fact, she says yes, but she doesn't actually talk. We tell her to replace that interval with this interval, right? Good. So what we have to prove now that what she's holding is consistent, right? It's consistent with what the algorithm did before. It's consistent with the new step, right? So this was consistent with the previous steps, and we made sure it was consistent with the new step as well, and right, and we made sure that we didn't mess up these previous guys. Right? How do we know we didn't mess up these previous guys? It's because, right, because we told her to drop something that covered this point, right? And we know the algorithm hadn't covered that point, right? Because that was the first uncovered point, right? So we didn't mess up what was consistent before, and it was optimal. Is it still optimal? So this is still optimal because we just dropped one interval. All right. So now the question, is it valid? We want to know, does what she had before was valid? Right? We need to prove that what she's holding now is valid. What does valid mean? Is it covers all the points. Everybody, right? How do we prove that it covers the points? Let's consider the 3 types of points. These earlier points, how do we know what she has covers these points?
Because we have it.
Right? Because we've covered them. She's consistent with the algorithm. We haven't messed that up. She's covering that. Right? Good. How do we know that she's covering this guy?
Because you told me that.
Because we put that one in there. Good. How do we know she's covering these ones?
Because she had no solution.
she was covering them before, and we replaced, right? We're not worrying about this already. We already covered that. Does it cover those? Well, we replaced one that goes furthest to the right with somebody who doesn't go as far to the right, right? So, if anything, we're covering these better than we covered them before, right? Does that make sense? Our interval extends further, at least as far to the right, right? Right, of the ones, right? So we proved that what she has, you know, we started off with something that was valid and consistent with what the algorithm has done so far and optimal. We massaged to this. We proved that this is still valid, it's consistent with what the algorithm had done, and consistent with the new step that the algorithm did, and it's still optimal. And hence the loop invariant has been maintained. Everybody good with that? And then we keep going. How many minutes do we got? We got any? One. All right. 1 minute. I'm going to talk about another nice data structure for solving problems. And it's a lot of problems can be solved by having events come, right? You have these events come, and you have a queue of events, and you handle the events as they come. All right. So this is we're going to do this event handling thing. We're going to slide along here and have events. We come along here. We hit this edge right there. What do we say about these events? Oh, look it. We started an interval, so what we're going to do with it, we're going to put it in the queue. It's in the queue. Then we slide along, we put it in the queue. Right? We slide along, we see this guy. It's not covered. So what do? These are the guys who might possibly cover it, right? So we choose one of them, right? Then we go along to the next guy. We put it in the queue. We go here, we see it needs to be covered. Oh, it's covered already. We come over here, it's covered already. Now, this interval is over, right? That's kind of an event. What should we do?
Drop it.
Do we need to drop it? We could drop it, right? We could drop it, but do we need to drop it? Because in the future, where is this going to be in our priority queue? It's going to be way down, right? Because it doesn't fall far to the right. So we're going to be ignoring it anyway. So let's not waste our time by taking it out of the queue. Let's just leave it in the queue. If it ever comes out of the queue, we're in trouble. Right? Because it doesn't cover the points that we want. Right? So we leave it in the queue. Then we go along to the next event. We put that in the queue. Now this is covered, so we go along. This goes in the queue. This needs to be covered, so we cover it. Everybody kind of follow that? And we just keep going, and that's the algorithm.
When we cover it, do we know the end of that line? And why are we picking that one instead of the small one?
Oh, because when we put them into the priority queue,
We know how long it is.
we put them, we know its end.
Okay.
So we put it in the priority queue based on its end. Right, when it starts, we say, hey, excuse me, when do you end? And then we put it in the priority queue according to that. Exactly.
Cool.
Everybody good with that? So I'm pretty sure that we are now done greedy algorithms. Yeah, look at that. Greedy algorithms. So, what are we going to do on Monday?
Test.
No.
No, let's not have a test. I haven't even started thinking about it. What are we going to do on Monday?
Dynamic.
Dynamic programming. Have a great weekend.